Hey class, welcome to the fourth video lecture of quantum mechanics, atomic structure. Today we will be talking about postulates of quantum mechanics. This was last class question. Estimate the wavelength accelerated from the rest of electrons, wavelength of electrons accelerated from the rest through a potential difference of 40 kilovolts. And here what is given, that energy equals to p square upon 2me, whereas p is the momentum and which is equal to ev. Now what is given, let me write the given things. What is given, E is equals to p square upon 2me, where me is the mass of the electron. So I can write this as, it implies P is equals to 2me E. Here E is given as, which is equal to electron volt. So E is equals to electron volt, E into V, not electron volt, E into V. So substitute that in this equation. P will become obviously P square will become 2me E into V, and P will become 2me E into V. This will have a power of half, or I can say under root, where m is the mass of electron, E is the charge on electron, V is the potential difference. Fine. Now what has been asked, lambda equals to, or the wavelength. According to de Broglie's wavelength, lambda equals to h upon p, where lambda equals to, h is 6.626 into 10 raised to power minus 34. This is in joule seconds, and put the values of p. P will become what? 2 into mass of electron, m. Mass of electron is 9.1 into 10 raised to minus 31 kilogram, multiplied by charge on electron 1.6 into 10 raised to power minus 19 coulomb, multiplied by V is 40 electron volts. So 40 into 10 raised to 3 volt, 40 kilovolt. See, V is given as 40 kilovolt in the question. Now let us first cancel the units. What I know, that joule is kilogram meter square per second square, and this is kilogram raised to power half. Is obviously this whole thing is in power of half. It is in under root, and this will become coulomb volt. 1 coulomb volt equals to 1 joule. This is again a new interconversion that you should know. Multiplied by, and this will become kilogram meter square second square, kilogram meter square per second square. This thing raised to 1 by 2. So if you cancel out the unit, it will come out to be in meters, and you calculate the units. What I have calculated is, it is 6.1. My answer is coming out to be 6.1 into 10 raised to power minus 12 meters. You calculate it and try to match your answers with this question, with this question's reported answer. Now let me quickly do the recap of what we have seen in the last class about the quantum mechanics. At first, what is quantum mechanics? Quantum mechanics is the theory. It is a philosophy. It is a theory that describes the dynamics. Dynamics is what? Motion. Dynamics of matter at microscopic level. Second, it is an invisible world. Theory is based on assumptions called as postulates, and these postulates are unproven and accepted, and they are not questioned, like de Broglie's wavelength, de Broglie's hypothesis, and Schrodinger's wave equation. This is important. Observables are obviously what? Kinetic energy, potential energy, etc. can be determined by using interplay of wave function determined by equation and operator defined for every observable. So for every observable there is an operator which is defined, which is core area of studying quantum mechanics. Next, what we saw Schrodinger's wave equation. This is time independent. Schrodinger's wave equation. This is time dependent SWE. Next, we saw Born interpretation. Born interpretation tells what? That psi square, modulus of psi square is probability density, and this modulus of psi square into d tau tells about the probability of finding a particle in a given region. Now, wave function, properties of wave function. Which are the wave functions that are acceptable in quantum mechanics? Those wave functions which have single value, where a square is integrable, and they are continuous and they are finite. Must be continuous, have finite derivative, and have finite value and single value, then square integrable. These are the things we saw in the last class. Now, before going to the postulates of quantum mechanics, I want to give you a brief introduction about the operator. Now, what is an operator? It is a mathematical operator. A mathematical operator is a symbol that stands for performing one or more mathematical operations. Where operator can be dy dx, addition, multiplication, division. When the symbol of operator, yes, this is important. When the symbol of operator is written left of the symbol of a function, then operator is applied to that function. Let's say sin x is a function, and if I want to apply an operator, so that is written on the left side of the function. So dy dx of sin x. Now dy dx is what? It is an operator which is operated on the function sin x. Next, dy dx is a derivative operator standing for differentiation of function with respect to x. Now, operator we use in quantum mechanics, operator is written with a caret, or I can say cap. So yesterday we saw Hamiltonian operator, h with a cap. It was minus h cut square upon 2m d upon dx square plus vx. This was Hamiltonian operator. So Hamiltonian operator h over caret or cap. Now, the result of operating on a function with an operator is another function. Let us see in this scenario. A cap is an operator which is operated on a function giving another function, where g is another function. The symbol q is an abbreviation for whatever independent variables f and g depends upon. This can be elaborated by the figure 16.1, a function with its derivative. Let's say the function is ln of x. Okay, and if I want to operate the function ln of x, it will give 1 upon x. So 1 upon x is another function. So here there are two graphs. First, this graph, one graph is the graph of ln of x, and this graph is of 1 by x, this second graph. So when an operator is operated on a function, the result is another function. Now there is a whole complete algebra regarding the operators. Yes, there is operator algebra that you will be studying in the higher classes, but for at this juncture you should know that yes, operators do have their algebra, and there are some operator equations also, like this. A operator is operated on a function, B operator is also operated on a function. Now the function is the function is same. The function is same, f of q. Now, function is said to be a well-behaved function or a complete function only if A operator is equals to B operator. That means what? That the values must be two sides of the equation always produces the same result. Always produces the same result when applied to any well-behaved function. So it must give the same result when two operators are operated on the same function. Then I can say that the function is a well-behaved. So this is not in the in our syllabus, but at least you should know that yes, operators do have their algebra, and you have to do the operation on that function and find the value of that particular function. Now moving on towards the core topic, that is postulates of quantum mechanics. Postulates of quantum mechanics. There are ideally 6 postulates. Yesterday we saw a brief when we were moving towards the postulates, we saw some brief introduction about the postulates. The first postulate is see why postulates came into existence. Then we'll see the first postulate, why postulates came into existence. See, the Schrodinger wave equation does not provide a complete theory of quantum mechanics. Schrodinger wave equation is, although it provides almost all information about the particle or the wave, but it does not provide the complete information about the quantum mechanics. So, Schrodinger, Heisenberg, and other scientists devised several postulates. These postulates are assumptions which are not proven, but they are so true that their existence is unquestionable. And for non-relativistic quantum mechanics, if I elaborate it more, then quantum mechanics, one is non-relativistic and one is relativistic. Here we are studying non-relativistic quantum mechanics. In relativistic quantum mechanics, a scientist Dirac has contributed a lot, and there Dirac has contributed a lot, and there his contributions being studied. But at this junction, we are studying non-relativistic quantum mechanics. Now, foundation for non-relativistic quantum mechanics. In any theory based on postulates, the validity of postulates is tested by comparing the consequences of postulates with experimental fact. Quantum mechanics do pass this. Postulates of quantum mechanics do pass this. So for being a postulate, it has to be comparable with the experimental facts. And in quantum mechanics, the postulates do give satisfactory results, and therefore they are considered as a postulates. Now moving on towards the first postulate. Postulate first. See, the first two postulates that we are going to see, that we have already discussed, but at that time we were not knowing that these are postulates. So let me just quickly read it. All information that can be obtained from the state of mechanical system is contained in a wave function psi, which is continuous, finite, single-valued of time and coordinates of the particles of the system. This we have already seen that psi, the wave function, tells all the information about the particle of the system, which is continuous, finite, single-valued. This we already saw. So this is nothing but the first postulates of the quantum mechanics. Now this postulate implies this postulate implies one-to-one relation between the state of a system and the wave function. Now there are certain states of the system, n equal to 0, n equal to 1. If I am talking about an atom, so this first postulate provides one-to-one relation between the state of the system and the wave function. That is, each possible state corresponds to one wave function. Each possible wave function corresponds to one state. So for one state, there is a particular wave function, and for another state, there is another wave function. So each state of a system corresponds to a particular wave function, which is its unique identity. Next, moving on towards the second postulate. This already we saw. This is what this equation. This is Schrodinger's time-dependent Schrodinger equation, time-dependent Schrodinger's wave equation. H cap psi is equals to I h cut d psi by dt. What the second postulates tell, that the wave function psi obeys the time-dependent Schrodinger's wave equation, where H is the Hamiltonian operator of the system. So this already we have seen. This is nothing but it is second postulate. Now this also we have seen that psi depends on x, the coordinate, and the time. So here it is written that Q stands for all the coordinates of the particles in the system where the coordinate wave function psi satisfy the time independent Schrodinger's wave equation. Right. Now, not all the wave function consist of these two factors. Which are the wave functions that consist of different factors that we'll be seeing at a later stage. Now this is nothing, this is just a cartoon. Moving on to the postulate third. What it tells, there is a linear Hermitian mathematical operator in one-to-one correspondence with every mechanical variable. Now what is Hermitian operator? What is Hermitian operator? That is not concerned at this stage. You will be learning about the Hermitian operators in your higher classes. So I am skipping this postulate because there is a complete properties of Hermitian operators. If I will start, then I have to tell you that all the properties of Hermitian operators also. So you just keep in mind that yes, for every mechanical variable there exists a linear Hermitian operator in quantum mechanics. Next, fourth. Now start reading. If a mechanical variable A is measured without experimental error, the only possible outcome of the measurement are the eigenvalues. We have seen what are eigenvalues. Eigenvalues from eigenfunctions. Eigenvalues of the operator A that corresponds to A. A is the operator and corresponds to the A. Now, second, the expectation value. Expectation value is the one with this is the thing to calculate the expectation value. The expectation value for error-free measurement of a mechanical variable A is given by this formula. A is equals to given by this formula. A is equals to psi integral of psi A cap psi dq over divided by integral of psi star, this is complex conjugate of psi dq. Again I am skipping this postulate here because this is nothing. You just have to integrate this wave function and operate this wave function with a given operator and find the value. And the second, in the denominator, what you have to do, you have to multiply the complex conjugate of that wave function and the original wave function and divide it. That's it. So again you will be seeing this postulates in detail in your higher classes. So these postulates, you just postulate 3 Hermitian operator and postulate 4 the expectation, how to calculate the expectation value of an observable, that you have to just go through it. Now before moving to the next postulate, let's see some things about Heisenberg's uncertainty principle. This already you have encountered in 12th class. I am just repeating it, and we will see some other forms of Heisenberg's uncertainty principle also. At first, let's see what the Heisenberg's uncertainty principle tells us. What it tells, it is impossible to specify simultaneously the arbitrary position, both momentum and position of the particle. So it tells that it is impossible to determine both the position and the momentum of the particle simultaneously. Now before discussing this principle further, which is mathematically, this principle can be written like this: delta x is the position and delta px is the momentum, which is greater than or equal to h upon 4 pi or h cut upon 2, where we have already seen h cut equals to h upon 2 pi. h cut is reduced constant and h is Planck's constant. You know the value also. Now again coming back to this, now that if we know the position of particle exactly, then we can say nothing about its momentum. So out of momentum or the position of the particle, only one can be determined accurately. If any attempt has been made to determine the other, the first observable that has been determined, that determination becomes less accurate. The argument draws on the idea of regarding a wave function as a superposition of eigenfunction runs as follows. Now this can be illustrated by the graph that you are seeing here. See, psi over the position. This is a peak that you are seeing over here, which has zero amplitude. The amplitude is 0 in this peak. Fine. So read this. The wave function for a particle at a well-defined location is sharply spiked function that has zero amplitude everywhere except at the particle position. So here you can see the amplitude is, here amplitude is 0, here amplitude is 0, but at this junction amplitude is not equal to 0. So what it means that yes, at a certain position the probability of finding a particle is there, but the amplitude is 0. About the momentum, we cannot predict about the momentum. Now read this. The product of uncertainties of two conjugate variables. Yes, this was the principle that we have studied in 12th, but this is the general statement for the Heisenberg's uncertainty principle, because Heisenberg's uncertainty principle is not only valid for the momentum and the position. So two conjugate variables is always equal to or larger than h upon 4 pi, where h is the Planck's constant, and if we use that symbol delta x and delta px for uncertainties of the coordinate, then its conjugate momentum, then the uncertainty principle becomes this: delta x into delta px is greater than equal to h upon 4 pi. So it is not true that this principle is only valid for the position and the momentum, but any two conjugate variables are there for the uncertainty principle to exist. What are the two conjugate variables? Now let's move to that. Other forms of Heisenberg's uncertainty principle. That means other two conjugate variables. First, time energy uncertainty relation. Yes, this is what? Energy. This is time. Similarly, like position and momentum, energy and time also obeys the Heisenberg's uncertainty principle. So if an attempt is made to measure the energy, then the measurement of time becomes less accurate. Another thing, Heisenberg's uncertainty principle is also valid for angular momentum and angular position, where delta L is angular momentum and this delta phi, or I can say theta, is angular position. So Heisenberg's uncertainty principle is valid for this also. Now moving on to the fifth postulate. The fifth postulate of the quantum mechanics tells about the measurement and the determination of the state of the system. The fifth and final postulate. Yes, in quantum mechanics it is considered that it is the fifth and the final postulate. So immediately, let me read it first. Immediately after an error-free measurement of the mechanical variable A, in which the outcome was the eigenvalue Aj, the state of the system corresponds to a function that is eigenfunction of A and eigenvalue to Aj. Now when reading this it becomes complex, but let me write this. See what it tells, that after immediately after an error-free measurement of a mechanical variable A, in which outcome has an eigenvalue Aj. Mechanical variable is A, in which the eigenvalue is Aj. Right? And the state of a system corresponds to a wave function that is an eigenfunction of A which is corresponding to the eigenvalue of J. So I can say this. What it tells that yes, eigenvalue equation is followed in quantum mechanics. That this postulate wants to say eigenvalue equation is followed in quantum mechanics, and each eigenfunction has some characteristics eigenvalue that satisfies the eigenvalue equation. This was postulate 5. Now, what is the overview of the postulates? See, the first thing, quantum mechanics is based on the set of postulates. They are fundamental hypotheses or assumptions which are unproven. Second, the first two postulates establishes the role of wave function in quantum mechanics. The third postulate establishes the connection between each mechanical variable and mathematical operator. Fourth postulate. The fourth postulate provides means to obtain the information about the values of mechanical variables. And fifth postulate tells about the state of the system, in which state the particle is residing. So this is the physical significance of all the operators that we have studied, that we have discussed up till now. So we have discussed 5 postulates till now. Moving on to the 6th postulate, that is given by Wolfgang Pauli. Yes, the same scientist which gave the Pauli's exclusion principle. And as we will go in detail, you will see that Pauli's exclusion principle came from the postulate 6. The asymmetricity principle. Now, what is asymmetricity principle? The total wave function must be antisymmetric. See, this is important. The total wave function must be antisymmetric with respect to the interchange of all the coordinates of one fermion. What is a fermion? We have already seen in the first video classes. See, if you have not been through the 3 videos that I have uploaded, please go through it and then only come to this video class. Otherwise, you won't be able to understand anything. So please refer those 3 videos, then you come to this 4th video class. One fermion. What are fermions? Fermions have spin, half integral spins. With those, let me start again. The total wave function must be antisymmetric with respect to the interchange of all coordinates of one fermion with those of another. Electronic spin must be included in this set of coordinates. What it is trying to say, that the function has 2 parts. One is the space part and other is the spin part. The multiplication of the space part and the spin part should give an antisymmetric result. At this juncture, to tell you what is antisymmetric and what is symmetric is difficult, as you have not studied something about statistical thermodynamics and the atomic particle physics, but in the higher classes you will be able to see what is antisymmetricity principle. So at this junction, you just remember that there is another property of that function, that the function that is given by 6th postulate, that the function has 2 parts, the space part and the spin part, and overall the function should give an antisymmetric result. That is the 6th postulate of quantum mechanics. How I can explain this? I can explain this by, see, first read this. The wave function must be antisymmetricized to confirm the physical indistinguishability of the electrons. This leads to Pauli's exclusion principle. So I can explain this postulate by Pauli's exclusion principle. I hope you all know and you all have studied this Pauli's exclusion principle in your semester 1, that Pauli's exclusion principle is nothing, what it tells, no 2 electrons will have the same quantum numbers. They have different spins also. So that is Pauli's exclusion principle, which is a direct result of this antisymmetric principle. So from the antisymmetric principle, the Pauli's exclusion principle have been originated. Now that was all about the postulates of quantum mechanics. Now in quantum mechanics, I have already told in the previous video lecture that the motion is studied by models. There are certain models to study the motion. Motion, translational motion, electronic motion can be translational motion, motion can be electronic motion, motion can be vibrational motion, or it can be rotational motion. So all these motion can be studied in quantum mechanics with the help of models. There are certain models to study this, but in classical mechanics there are straight away formulas, so you can put the values in the formula and get the answer. So what are the models that are there for studying these motions? Let me uncover that one by one. Now, to study translational motion, the model is particle in a box. This box can be 1 dimension, 2 dimension, 3 dimension, or of higher dimensions. And to study the translational motion, we have a model in quantum mechanics, that is particle in a box. To study vibrational motion, we have a model, that is harmonic oscillator, to study the vibration of the harmonic oscillator, to study vibrational motion and to find its there are two things. First is energy, second is function, wave function, because wave function tells about the probability of finding the particle and gives all the information that where the particle is residing, and energy tells about the energy of any state, can be calculated. So for calculating the energy and the wave function for vibrational motion, the model harmonic oscillator is used. For rotational motion, a model rigid rotor is used. And for electronic motion, and to understand electronic motion, the model of hydrogen atom or hydrogenic atom is used. Yes, here I can use hydrogenic atom. Hydrogen or hydrogenic atom model is used to study the electronic motion. All the motions, whether it is translational, vibrational, rotational and electronic motion, that is in the syllabus of chemistry. When you will go to the higher classes, you will be deriving the wave function and you will be finding the energy for all the motions. But at this junction, there is only the introductory part of quantum mechanics. So that is it. Next, now to find the properties of system according to the quantum mechanics, we need to solve the appropriate Schrodinger's wave equation. Now this is the important thing that I want to focus on. Schrodinger wave equation can be solved. As you have seen, the Schrodinger wave equation is nothing, it is a differential equation. See, Schrodinger wave equation, if I write the Schrodinger wave equation is what? Schrodinger wave equation is a differential equation. Okay, and those of who have been through the mathematical background, they know or they have studied the differential equation. There is a complete chapter on differential equations. The differential equations can be solved by a method which is called as separation of variables or variable separation method. Those from bio background, they just know that yes, Schrodinger wave equation is a differential equation, and differential equations can be solved by a method which is called as separation of variables or variable separation method. Now before moving on to the solution of Schrodinger wave equation, you all know that coordinates are of two types. First is Cartesian coordinates, that is your x, y and z. Other coordinate system is polar coordinate system. I don't know whether you are aware of this or not. Polar coordinate system deals with r, theta and phi. These are the things that corresponds to the polar coordinate system, and Cartesian we are studying since the school days. It is x, y and z system. So now to solve the Schrodinger wave equation, the Cartesian coordinate system gives a messy results, and it is not possible to solve the Schrodinger wave equation in Cartesian coordinates. So Schrodinger wave equation is solved in polar coordinate system. Now how the Schrodinger wave equation solved, let me just give you an introduction about it. See, this is polar coordinate r, theta and phi. This is wave function. This can be written as this: r, capital R into small r, y in the braces it is theta and phi. So here you can see there are two terms. If I divide it here, you can see there are two terms. RR is the radial factor and y theta phi is the angular factor. So there are two terms. Both these terms have specific significance, and they give some certain important things that we'll be seeing at a later stage in this slide also. But these two are different. RR is the radial part and y theta phi is the angular factor. Now wave functions of single electrons are called as orbitals. We'll be seeing how orbitals look like and what orbitals are, what is atomic region is there. But at this junction, just skip it. We can choose between real and complex orbitals. Each complex hydrogen atom orbital contains phi m functions. If I want to write this in terms of this, I can write it like, as you can see on the screen, phi n l m is equals to r n l r theta l m and phi m phi. What it indicates that r, the radial part, consists of n and l. The theta part consists of L and M. The phi part consists of M. When you solve the Schrodinger's wave equation, the equation becomes of this order and it transforms into two variables or two parts. One is the radial part and other is the angular part. The radial part gives information about N and L. The angular part gives information about L and M. Now, as you know that N is the principal quantum number, L is azimuthal quantum number, and M is the magnetic quantum number. But these equations, the solutions of Schrodinger wave equation, gives idea about the quantum numbers. Before going to quantum numbers, let me read this. The radial factor are a set of functions with two quantum numbers, again N, principal quantum number, and L, the same quantum number as in the spherical harmonic motion. So spherical harmonic function. Now this thing, theta and phi, this thing is called as spherical harmonics. The angular part. Next. So what I want to convey is that take the Schrodinger equation, differential equation, solve it by variable separable method, and you will end up with quantum numbers. Which quantum numbers? N, L and M, L. These are the three quantum numbers that can be obtained by the solution of Schrodinger wave equation. Now what about the fourth quantum number? The spin quantum number. Yes, this cannot be obtained from the Schrodinger's wave equation, but if you know the three quantum numbers, then it becomes easy to calculate the spin quantum number. Or let's talk about the spin quantum number. The spin quantum number ms, this is in subscript. Ms describes the angular momentum of an electron. An electron spins around its axis, has both angular momentum and orbital angular momentum, because angular momentum is a vector. The spin quantum number has both the values, half in positive or negative. What it is trying to say that this is nucleus and this is electron which is revolving around the nucleus. Now electron has its own axis in which it is revolving, and it is also revolving around the nucleus also. So there are two motions. This is like a solar system, like Earth. Earth is rotating around its own axis and revolving around the sun. Similarly, electron is also rotating around its own axis and it is revolving around the nucleus. So it can have both angular momentum and orbital angular momentum. So that is an indication of ms, where ms is what? The spin quantum number. So spin quantum number is typically a different thing that cannot be derived from the Schrodinger's wave equation, but you can get an idea of N, L and ML from the Schrodinger's wave equation. Now, as we are discussing quantum numbers, let me quickly recap what are the quantum numbers that you have studied. First is principle. This, I think you have already studied this in first semester, but just discuss it now at this junction also. First is principal quantum number. Principal quantum number determines the orbital size and the energy and accounts for the main lines of atomic spectrum. Azimuthal quantum number, it determines the orbital shape and it gives information about the fine lines in this atomic spectrum. Magnetic quantum number, it tells about the orientation of the orbital in space. It tells about the splitting of lines in atomic spectrum. MS, spin quantum number, gives the particular value of plus half minus half. It tells about the magnetic properties of substances. So these are the 4 quantum numbers that you are well aware of. And at this junction, what we have seen the origin of quantum numbers. That these 3 N, L, M and MS are derived from Schrodinger's solutions of Schrodinger wave equation, and MS is derived from the spin quantum number. Next, here this is a simple diagram to indicate or to understand the quantum numbers in a better way. This you are well aware of. This is what nucleus, N is equals to 1, 2, 3, 4. These are shells. S, P, D and F, these are the orbitals that we'll see in the next video class how these orbitals look like. And these orbitals have certain value of L. These orbitals have certain value of N also, and they have calculated the value of ML. Moving on, what we have discussed today. First, we saw operators. What are operators? Operators are nothing. They operate on the observables and operates on the function and give the values. They operates on function and give the values. There is a complete operator algebra regarding the operators that you will be seeing in the higher classes. Second, what we have seen 6 postulates of quantum mechanics. The first 2 postulates we have already seen. The third and fourth and fifth and sixth postulates, expectation value postulate and the linear hermiticity postulate, is just you should have an idea that yes, these 2 postulates are there in quantum mechanics, because that is not in the syllabus, but you should be aware of that postulates also. Next, Heisenberg's uncertainty principle. This you have already studied. That delta Px is greater than equals to h cut upon 2, or I can say delta E into delta T is greater than equals to h cut upon 2, or delta L into delta phi is greater than equals to h cut upon 2. These are the various forms of Heisenberg's uncertainty principle. Next, quantum numbers and their origin, that how quantum numbers have been originated and what is the significance of the quantum numbers that we have seen very quickly. And you should know that how quantum numbers have been originated. It has been originated from the solution of Schrodinger wave equation, which is a differential equations, and the differential equation is solved by variable separation method. And when the equation has been solved by the variable separation method, you get 2 things. One is the radial part and other is the angular part, or I can say spherical harmonics. And radial part gives the value information about N, L, and this gives information about L and ML. And there is another quantum number also, which is the magnetic spin quantum number. Now this is today's question. You have to find the shell or subshell for all of these 5 sets of quantum numbers. Stay home, stay safe. Thanks for watching. Now in the next class, we'll be arriving at the shapes of orbitals. This will be the last class of atomic structure. Then we'll be seeing only the questions. So now only 2 classes are remaining. In one class we'll be discussing the shape of orbitals, and in second class, or if not required, this will be the last class of the atomic structure, shapes of orbitals, and that we'll be seeing I'll be sending the question bank, or we'll see the questions. If time will permit, we will see questions in another class. So that will be all. Now I require at least 1 or 2 video class for completing the atomic structure. Thanks for watching. If you have any doubt, you can comment or WhatsApp or mail me. Stay home, stay safe.